M was defined to be this. A squared across, sorry, C hat e to the I k dot r. It was defined to be this. And what matters, as I said before, is ks cross z hat e to the I k dot r. So if I normalize it, I will want this to be 1 or to be equal to a delta function. I want this to be a delta function, right? So then what happens is that I should pick my normalization such that this will become kz dot kz is ks squared, something. So I would want to define this thing and divide by ks. If I divide by ks, it will become normalized. Let me leave the 2 pi in there. Okay, let me leave 2 pi in there. So it becomes normalized. So if m is normalized, you can show that n is 1 over k curl of m, and then n dot n is 1 over m. N dot n is 1 over k curl of m dot curl of m. Okay, it's equal to that, and then you can do integration by parts and show that this is equal to curl cross m dot n m. After doing integration by parts, okay, this is rather sloppy here. Okay, do integration by parts and move on to the curl over to the m, and this is just k squared m. So this is m dot m. So there are integration by parts involved, there are integrals involved. I just didn't write them down. So if this is normalized, this will also be normalized. That's what it says. And you can show that you can normalize the L by dividing by k, you get a normalized L. So if you divide the k, like my L was defined to be equal to ik e to the ik dot r. I divide by k. This becomes a normalized L. And all this would become normalized. And what happens then is that ks will disappear from here, ks will disappear from here, k squared will disappear from here. And then you even have a more succinct form of the Dirichlet-Green's function. And another way to write this succinct form of the Dirichlet-Green's function, if things are normalized, is that you can write it as such. The Dirichlet-Green's function is nothing but an integral summation of all the vector wave functions that you can find at k, r. And the other one is always the complex conjugation of k, r over k squared minus k squared. This is a normalized. And you often find that in textbooks as well. The normalized form of the Dirichlet-Green's function is just written in that form, where f is assumed to be normalized. In that case, f can be m, n, and l. And in the case of, it's not time yet, right? It's 5 more minutes. So in the case of normalized vector wave function, that is a very succinct form of the Dirichlet-Green's functions that sometimes you find in textbooks. Okay. When they write in that form, they actually mean this form. This is more detailed. Okay, and then the issues arise as well as that these integrals are not well defined because the poles that you have on the ray axis, when you try to integrate this, we encounter poles. So what do we do in order to evaluate those Fourier integrals? Mike, you remember what we did?
What was the question?
Oh, yes. I saw you grinning, so I thought maybe you know the answer. So there's a pole right at the origin, not at the origin. When k squared equals k naught squared, right? There's a pole. Those Fourier integrals are actually undefined. So we have to do something.
For the Riemann sheet.
No Riemann sheets yet.
Some laws.
Yes?
Some laws.
Introduce infinitesimal laws. Okay? So you try to introduce some laws. So k naught squared is omega squared mu naught epsilon naught. You can make this into something lossy, and then this will have an infinitesimal small imaginary term. And then when k squared is real, it will never encounter that pole. And then everything is well defined. And you have to introduce laws in this manner. And this corresponds to finally a solution that satisfies the radiation condition. You can only have outgoing waves. You cannot have incoming waves. Those incoming waves will be exponentially larger at infinity. So if you introduce an infinitesimal loss like that, this kind of Green's function is also called a retarded Green's function, because it can only admit outgoing wave solutions. So in literature, this would be known as a retarded Green's function if you introduce loss in this manner, because you push the pole slightly away from the ray axis, and the solution is either called a retarded Green's function, the Green's function that satisfies a radiation condition or some of the radiation condition, or what is another term for it? Retarded Green's function that satisfies the sum of the radiation condition. The causal Green's function. Okay? So all this means the same thing. Causal, retarded doesn't mean stupid here. This Green's function is actually quite smart. And then it's satisfying radiation condition. Okay, all these three terms mean the same thing. So if you read the literature and hear about these three terms, it meant the same thing. And if you have picked the loss to be active instead, then the pole will start to move slightly below the ray axis. That would be called the advanced Green's function. Very smart guy, right? Opposite of retarded is advanced. So the other one is called the advanced Green's function, or non-causal Green's function. And you do see that written up in the literature sometimes. Retarded Green's function, advanced Green's function, and this kind of thing. Okay? Okay, are there any questions regarding this Green's function? I think later in the course, I'd like to prove something, if I have time, that the imaginary part of this Green's function actually corresponds to the local density of states of the photons that you have in a system. Okay, so one of the things that is quite interesting is, in fact, that since I have a few more minutes, I don't have time to start a new topic, which is that if I have something like this, k squared minus k naught squared plus I eta, or minus I eta, if I introduce a little bit of loss like this, okay? And if I take its complex conjugate, I will get something like this. If I take something plus this or minus this complex conjugate, I get the imaginary part of the entire thing. If I take the thing, and this is the same as imaginary part of this thing. Okay, it's the same as that. And then this is the same as I eta of k squared minus k naught squared plus eta squared, right? You just complete the square in the denominator, you get that. So this is just eta over k squared minus k naught squared plus eta squared. And do you recognize what this function is when eta goes to 0? that function is actually quite important. Does anybody recognize what that function is? If I plot this function as a function of k, okay, if I plot that function, when k is equal to k naught, it becomes 1 over eta squared, right? When k is not equal to k naught, it's very small, so it's a function that looks like that. What happens if eta becomes smaller and smaller? The peak will become bigger and bigger. The peak is 1 over eta, right? You look at this function. So it is actually a limiting, a function that eventually becomes a delta function when eta goes to 0. Okay, so if you have a Green's function, this is a retarded Green's function, this is a advanced Green's function, you add them together, you get something that actually is something that looks like the delta function. So if you add something called the complex conjugation of this to itself, you go through this kind of manipulation, or you get finally the interesting, very interesting formula that the imaginary part of this static Green's function is equal to 1 over 2 pi q k f of k r prime f of k r. So this should be r prime. This should be r prime. Okay, times the delta function k squared minus k naught squared, because this is actually a delta function, and this is something called the what is this called? It's a complementary function or something. When we make r equal to r prime, this becomes like the local density of states. So the imaginary part of the Green's function, when r equals r prime, becomes like the local density of states of the photon states, and so on. Okay. So maybe someday I'll go through that if I have time. Go to that in greater detail. So the Darby Green function is essentially very interesting. And if you take an imaginary part, it has some relationship to quantum mechanics and the fluctuation dissipation theory, and that you can actually relate it to. Okay. But if you take this local density of states are defined for photons, and it actually becomes quite useful. Okay. I guess we'll stop here and continue next time.